morning to all. Today I will discuss about solidification of casting under Unit 2. And end of this lecture the student will able to learn the concept of solidification of metal and alloy and also problems on solidification time. We will find out using some formula. Introduction to solidification. In case of solidification, if the solidified product will take proper solidification, directional solidification, so the final product will be defect free. Okay. Then second one, the metal is poured when the mold cavity, and at that time the molten metal start the solidification. And during the solidification, some cohesion and properties and some structural properties and also changes in that particular solidified product also. Another, during the solidification of the solidified product, after pouring the molten metal into the mold cavity, during solidification, during directional solidification, some metallographic structure will be changed. Some metallographic structure will be changed, and in that particular metallographic structure depends upon the or consists of that particular metallographic structure, grain size, shape, orientation, and other things, distribution of alloying elements. Because more than two elements we have molten, and then we pour of that particular material, and after mixing, the distribution of that particular parent materials, that also depends upon that will be also changes some metallographic properties of that particular solidified product. Another, underlying crystal structure and imperfections. Sometimes if that parent metals will mixed properly to that particular mold cavity, so good metallographic structure will be created, and also any defect or any imperfections does not create to that particular material. If it will does not distributed and does not mixed to that particular parent metals, so solidified product may be defective product will be created, and also some imperfections also created to that particular solidified product. Generally, in case of volume shrinkage and volume contraction occurs during three stages. First is liquid contraction, means liquid contraction when occurs when metal will liquid state, means when we pour in the molten metal to that mold cavity, so at that time some liquid contraction will be started. Okay. Another is solidification contraction, means solidification contraction occurs when pouring the molten metal to the mold cavity, means the solidified product changes its phases from liquid to solid, means the shrinkage will be occurred to that particular product, means solidification contraction also occurred. Another is solid contraction shrinkage, means when metal is takes solid, means fully it will converted from liquid molten metal to solidified product. So in that cases, the after solidification, the shrinkage, means some voids will be created to the final product, means shrinkage will be created to that particular final solidified product, means solid contraction also occurs. That is the some picture. In that picture we have seen that is, if we consider that is a pattern. Okay. Using that pattern we created the mold cavity. Okay. And that is the pouring basin, and that is the sprue. Through that sprue, the pouring molten metal comes to that particular mold cavity. And when pouring the molten metal to that particular basin, so it will come to that particular cavity, and it will fill up throughout the mold cavity, Okay. After fill up to that particular mold cavity, then it will start its solidification. Means from that particular mold surface, first heat will be extracted from that mold surface, and due to heat extraction from that particular mold surface, at the surface contact, first solidification start. First solidification will start it. Then it will goes towards the center. Okay, means due to that thing, then total solidification will take place to that particular mole cavity. Okay, after solidification, we will remove the pouring basin, sprue, mold box, and other patterns, and some core pins we will remove. Then finally we have got the particular final product. Okay, after solidified product we have got. Concept of solidification. What happens in case of solidification during casting time? What are the solidification means? What are the concept of solidification during casting? So first, a molten metal will pour to the mold cavity. That pouring molten metal possesses high energy because the molten metal solidified product converted into molten metal means it has heat, means it has possesses high energy. Okay, then molten metal cools. When molten metal means comes to the mold cavity, then it extracted means heat will be extracted or heat will be removed from that particular liquid metal. Then it will convert it into solidified product. When heat will be extracted from that liquid metal, means in that cases the heat will be removed, means energy will be lost. So after losing the energy, it will form to crystals. When heat extraction, it will be started from the mold walls, and from the mold walls it will start the solidifications. Okay, and then it will goes towards the center. Means when the mold walls, then any other places, first metal crystals called nuclei, means heat will be extracted from the mold surface, then it will start the formation of the nuclei. Then nuclei formed above to tend to go second stage of solidification. Then it will grow to second stage of solidification. Means the crystal growth, means it forms the nuclei. Then it will be converted into crystal. That crystal growth acts like occurs at a dendrite manner. The crystal growth acts like a dendrite manner. Then dendrite growth takes place the evolution of small arm on the original branches of individual dendrites. Means due to continuous formation of the dendrite structure, then it will form a arm of individual dendrites. Then it will, after continuous individual dendrites formation, then it will together, then it will combine and it will form the grains. Means due to continuous heat removal from that mold surface, then grain again and again it will be combined, and then it will be finally converted into final product. So slow cooling makes the dendrites to grow long. Means slow cooling rates forms the long dendrites, and fast cooling rates forms the small dendrites. Short dendrite growth will be awkward in case of slow cooling. Slow cooling, it will form the long dendrites, and in case of fast cooling forms the short dendrite growth. Okay, another dendrite becomes grain, means continuous formation of the dendrite, it will convert it into grain. Okay, slow cooling results in forms the higher huge grain structure, and fast cooling rates forms the lower dendrite structure, means lower grain structure. Okay, now we are seeing that if solidification proceeds, more and more arms will be grow, means more and more arms of dendrites it will be formed, and then again and again formation of the arms of the dendrite, it will convert it into grains. Then formation of again and again formation, then it will be combined and it will finally produce the solidified structure. So we are seeing that in that particular, that type of dendrites will be formed, dendrite structure will be formed, that type of dendrite structure will be formed. Arms type dendrite structure will be formed in that particular solidified product. Okay, so we have seen that things in optical microscope. So we have seen that type of arm type arm type dendrite structure we have seen in the particular optical using optical microscope. Solidification of pore metals. So in that cases we have known that pure metals generally possess excellent thermal conductivity and excellent electrical conductivity. Okay. Another, these metals also has higher ductility property, higher melting point and lower yield point, and also it has lower tensile strength also. Okay, that are the some important properties of the metal. Another important property, better corrosion resistance and compared to alloy. It has good corrosion resistance properties also. Good ductility property, good thermal conductivity, good electrical conductivity, that properties maintained to that particular pure metals. If metals has high melting point, so some difficulties will be exhibit to that particular pure metal. So what happens? Difficulties during pouring. When we pouring the particular that metal, so some difficulties we are facing. Another, the several metal mold reactions. Sometimes some metal mold reaction also occurred. Means mold surface is that in that particular mold surface maybe some reactions will be occurred when we pouring the pure molten metal. Greater tendency towards cracking. Sometimes cracking also form when we pouring the molten metal. After sometimes it will start solidification. After in that solidified product maybe cracking takes place. Another mode of solidification which may produce defective casting. Means when start the solidification, after solidification the metallographic structure may be defective. Means finally the product will be produced that may be defective product will be produced. So we are seeing that is the graph of pure metal solidification graph. What happens in that particular graph? That is the pouring temperature. Means in point A, the pouring molten metal pouring to that particular pouring basin and it will come to the mold cavity. Means in that pouring temperature the molten metal maintains its fluidity property, and then when it will decreases the temperature from A to B, it will come to the means it will reduces the means it extracts the heat. Means due to continuous heat extraction, what happens? Then the molten metal comes to the point B. Means it will start the solidification. Okay. Means in that cases we have seen that y-axis represents the temperature. Okay. And x-axis denotes the time. Okay. Means when it loses the heat from point A to B, so in that cases means it will goes to solidification. Okay, it will bring to solidifications. Means it start the solidification. So what happens? We are seeing finally means liquid metal cools from A to B. Okay, then from B to C the metal liberates latent heat of fusion. Latent heat of fusion means it will changes the phases of that particular molten metal. Means liquid molten metal converted into solid product. Okay, means in that cases temperature remain constant. Okay, then liquid metal starts solidification from point B. Means start solidification from point B. Then partly solid and partly it will remain as a liquid state. Means partly solid at any point between B and C metal is purely solid. Means between phase B and C, partly some part of the pouring molten metal will be solid and some part of the pouring molten metal it will containing as a liquid state. At point C, it will fully solidified product will be produced. Means equilibrium freezing temperature at that point it will fully completed into solidified product, and that time that is called local solidification time. Means from point B it will start the solidification. Okay, it will start the solidification. Means thermal arrest means continuously heat will be decreased, and due to continuous heat extraction, the solidification will be started from point B of the particular molten metal, and point C it will fully converted into solid metal. Okay, and that is the local solidification time. Up to point A to point C means that is the total solidification time. Means the molten metal maintains fully fluidity property at pouring temperature, means at point A. Then at point C it will fully converted into solidified product. Okay, means that is the total solidification time. Okay, and also we have seen that the cooling rate that will be denoted by capital D by small t, means that is the slope. That is the slope. Slope means here capital D means that is the capital T, and that is the capital T, and that is the small t. Means we know slope means tan theta equals to y by x. Theta equals to tan inverse y. Y means here capital T and x means small t. That is the cooling rate. As a slope we have denote the cooling rate, that is the capital T by, we know tan theta equals to y by x. So theta equals to tan inverse y by x. So using that formula we find out the cooling rate, means slope we have find out using that formula. Here y means that is the capital T, means along the y axis, and small t is across the y axis. From C to D, solid metal cools and tends to reach temperature, means already the metals pouring molten metal fully converted into solidified product at point C. Then that solidified product now coming to the particular room temperature. Okay, then the slope of AB and CD depends upon the specific speed of the specific heats of the liquid and solid metals. Means the slopes means cooling rate across the from point A to B. Here cooling rate depends upon the specific heats of the liquid and solidified product. Now solidification of the alloy. So in that cases we have seen that the alloy materials possesses some particular properties, means it has higher tensile strength, but in case of metals it has lower tensile strength, but it has higher tensile strength. Then better high temperature strength, means it sustains the higher temperature. Another better corrosion resistance, means it is a corrosion resistance material, means does not form the any oxides to the particular reaction with the oxygen. Another improved machinability and workability also increases. Another has lower melting points. Another improved castability. That are the maintained properties of that particular alloy. So main types of alloy is solid solution alloy, eutectic alloy, and peritectic alloy. That are the mainly alloy elements. Main types of alloy, that are the mainly three types: solid solution alloy, eutectic alloy, and peritectic alloy. So using that graph we are seeing that is the along y axis it denotes the temperature, and x axis along the x axis it denotes the time. Along the x axis it denotes the time. Okay, so in that graph we have seen that from point A, B, C, D. Okay, so in that cases we have seen that it will maintain the pouring temperature. It maintain the pouring temperature. Pouring temperature, that is the liquid state. And that state is the liquid plus solid, and that stage is the solid state. Solid stage means that is the A solid and that is the liquid. Means A is the pouring temperature, means that in that point A it maintained the fluidity property, Means pouring temperature, the molten metal maintain fluidity properties. When the temperature will be extracted, then it will come to the point B. Means it will be started the heat extraction. Okay, means from point B it will start the solidification. Means some part, means between B and C, some part will be solid, some part will be liquid state. Means that state denotes the liquid plus solid state. From at point C it will completed to the solid state. After comes to that solidification state, means it will extract the heat, means it comes to the room temperature. Means at point D fully converted into solidified product at room temperature. Okay, that is the main curve in case of alloy. Okay, that is the solidification curve for alloy. Here what we have seen, that particular curve, from A to B the alloy is a liquid state. From A to B it will liquid state, means it extract the heat. Solidification start from B and it will be complete at point C. Okay, means at point C it will convert it into solidified product, but temperature will be higher. Unlike pure metal, solidification occurs throughout the temperature. Means from B to C. Means it will remove the heat, means it will extract the heat. Means due to continuous removing of the heat, it will start to solidification. Latent heat will be liberated from B to C and tends to increase the time required to the solidification. Means continuous heat removal, the liquid phase converted into solid phase, but here temperature will be constant. That is the main discussion of the cooling curve for alloy. Now already we have seen that previous lecture. If we are consider that is the mole surface, that is the mole surface. Okay, then we pour the molten metal to that particular mole cavity. Okay, then after heat extraction from through the mole surface, that type of chill zone will be formed. That is the chill zone will be formed throughout the mole surface, because heat will be extracted first heat will be extracted from the mole surface, then chill zone will be formed. Okay, then after again and again heat extraction, then what happens? Now columnar zone will be formed. That type of columnar zone will be formed. Means that is the perpendicular grain. That is the perpendicular, means that is the columnar, that type of, means that is the columnar zone. That is the columnar zone. That zone is the columnar zone. Okay, after heat removal, then equi-X zone, means that is the equi-X zone. That is the equi-X zone will be formed to that particular mole cavity. Okay, means after removal of the heat from the mole cavity, then it will convert it into solidified product, and then shrinkage, means some voids will be created to the particular mole cavity. Means that type of shrinkage will be happen. That type of shrinkage will be happen. Means after pouring the molten metal, it will take fully fill up throughout the molten metal. Means after solidification, that type of, due to shrinkage, that type of surface will be formed. Okay. Now we are coming to the discussion of the particular solidification cases when skin thickness increases to form a shell around the molten metal as solidification progress. Means continuous heat extraction from the mold surface, the skin thickness increases. Means it will continuously converted into solidified product. Means here the solidification takes place. Means after solidification the skin thickness also increases, again skin thickness increases. Okay, then after removal of the heat, then skin thickness increases. Means continuous removal of the heat from the molten metal, the skin thickness will be increases. Then rate of freezing, means rate of solidification, it will depends upon the heat transfer into the mold as well as thermal properties of the metal. Means the heat extraction, it will depends upon the mold surface, and pouring of molten metal. Means depends upon the thermal properties of the metal and also heat transfer rate to the mold surface. Based on that, the rate of freezing means rate of solidification depends upon that thing. Another figure we have seen that grain structure in a casting of a pouring metal showing the randomly oriented grains of small size near the mold wall, means heat will be extracted, okay, and that type of grain will be created to that particular mold surface, means that grains are the oriented grains, okay, and after that heat extraction large columnar grains oriented toward the center of the castings, means continuous removal of the heat, that type of columnar grains will be formed. Columnar grains will be formed towards the center throughout the mold surface. Columnar grains will be formed towards the center for continuous heat removal from the mold cavity. Another thing we have seen that grain structure in case of in alloy casting showing segregation alloying components in the center of casting, means here that type of grain structure, that is that figure shows the in case of alloy, that type of grain structure will be formed to the mold surface, okay, then the columnar grains will be formed, okay, then again it will grains form to that particular middle zone, okay, in the center of castings. So solidification takes time, okay. So what will be that solidification of that molten metal? It will depends upon the volume of that casting and volume area of the castings, okay, means surface area, means heat transfer rate depends upon the area of that particular casting. That solidification time means here TST means total time required for casting to solidify after product pouring to the mold cavity, means when we pouring the molten metal to that particular mold cavity, then it will take some time to convert into solidified product, means that is the TST, total solidification time. So TST, total solidification time, depends upon size and shape of the casting. That will be that relationship correlated by scientist Corniff's, okay. Actually that rules is called Corniff's rule. What is the Corniff's rule? TST, total solidification time. Total solidification time equals to Cm V by A whole to the power N. Here TST means total solidification time, Cm is the mole constant, V means volume of the casting, and A is the area of the casting. Here N is the exponent. Generally it is taken as 2. Cm, mole constant, depends upon the mold material, thermal properties of the casting of the metal, and pouring temperature relative to melting point. Cm, mole constant, depends upon the mold material, thermal properties of the material, metal, and pouring temperature relative to melting point. That factors means Cm depends upon that particular factors. Value of Cm generally it is decided generally based on experimentation. That data already have taken previous operations carried out by the using same mold material, metal, pouring temperature. Based on that we have decided the value of the Cm. Again, a casting with a higher volume surface area ratio cools, means area of the mold surface is greater, so heat extraction rate also higher, okay, and easily heat will be extracted, and also the area means pouring molten metal and easily converted into solidified product. Another, to feed the molten metal to the mold cavity, total solidification time for riser greater than total solidification time for main casting. So it is a very important point to feed the molten metal to the mold cavity, total solidification time for riser must be greater than total solidification time for casting, because the molten metal, first molten metal will be converted into solidified product in the mold cavity. Then the solidification start with the riser, because after solidification to that particular mold cavity, the void will be created, means shrinkage will be created. After creation of the shrinkage, the molten metal comes from the riser. Okay, and after coming to that particular mold cavity, it will converted into particular solidified product. Then it will take the solidification to the riser. Otherwise, if first solidification takes place to the riser, after shrinkage to the mold cavity, the molten metal does not come to that particular mold cavity. That's why the total solidification time for riser must be greater than total solidification time for casting, main casting. So in case of riser and casting, mole constant will be equal. Generally the mole constant Cm, generally in case of casting and riser, same. Design the riser to have larger volume to area ratio so that the main casting solidify fast. Means that is also one another important. Design the riser to have a larger. Design to the riser to have a larger volume to area ratio so that the main casting solidify fast. Means if we are taken volume area ratio more to the riser, so easily the molten metal comes to that particular mold cavity after solidification. Okay, another, this minimizes the effect of shrinkage. Means the volume of the area, volume by area ratio if greater in case of riser than casting, so easily molten metal comes to the mold cavity. Means it minimizes the shrinkage effect. Means it will take the total mold cavity shape and it will finally, as per mold cavity shape, finally it will convert it into solidified product. So we are seen that to that particular starting level immediately after pouring, means after pouring the molten metal, it will take that shape. It will take that shape. Okay, that is the pouring molten metal, and that is the mold surface. That is the mold surface. Okay, that is the mold surface. Okay, then reduction level means after solidification, we have seen that starting level of molten metal immediately after pouring, means when we pouring the molten metal, then reduction in level caused by the liquid contraction during cooling. After cooling, we have seen that the level is reduced, means that is the starting level, then here level is reduced. Okay, so due to liquid contraction, means that is the liquid contraction takes place. Okay, initial solidification at mold wall, means when it will start the solidification, that type of shrinkage will be also occurred across the mold surface also. Means that type of voids will be created due to after means after heat extraction it will started the solidification, and that type of voids will be created, means shrinkage will be created to that particular solidified product. Then what happened? Reduction height due to solidification shrinkage. Due to solidification shrinkage, again it will convert it into solidified product. Again the height is reduced. Again height will be up to that height it will remain. Then again the height will be reduced. Okay, after solidification. Means reduction in the height and formation of the shrinkage cavity caused by the solidification. Means after solidification fully it will convert into solidified product. After fully conversion into solidified product, again height will be reduced. Further reduction in height and diameter due to thermal contraction during cooling of the solid metal, again means again heat will be extracted from that particular solidified product. So due to continuous heat extraction to that particular product, the diameter also reduced and also height of that particular molten metal also reduced. Solidification shrinkage occurs nearly the metals, because the solid phase has higher density than the liquid state. Means the solidification will start from the mole surface, and when it will take solidification, the density of that solid phase is higher than liquid phases. Another, solidification cause a reduction in volume per unit weight of the metal. Means reduction will be takes place to that particular solidification as per weight of the metal. Okay. Again, some exceptional cases there. In case of cast iron, when containing C content, so in that cases graphitization during final stage of freezing causes expansion that counteracts volume decreases associated with the phase change. Means some exceptional case that in case of graphitization we are considering that thing. In case of shrinkage allowances, pattern mechanisms means after solidification some shrinkage will be created, means some allowances will be created. So during considering that thing, what we can do that, now pattern mechanisms account for solidification, shrinkage and thermal contraction by making mole cavity oversized. Means if we are creating the mole cavity size is doing the oversized. So due to oversized mole cavity, the final dimensional accuracy will be better. Means the product will be created as per required dimension. If we know the shrinkage of that particular metal is this, so we using that data we prepare the particular mole cavity shape. Means oversized shape we have produced. Means when we pouring the molten metal, it will take liquid contraction and solid contraction. Ultimately, the after contraction, the final product will be produced as per accurate shape. So pattern makers must be created the oversized mole cavity. Okay. Another, amount by which mold is made larger relative to final casting size is called pattern. Means finally we have prepared the as per required shape of the required size of the casting, that is called pattern. Okay. So shrinkage allowances means after contraction, liquid contraction and solid contraction, so some allowances will be created. Okay. So that allowances are generally taken linearly. Directional solidification. So to minimize the damaging effects of shrinkage, what we can do? Now, it is desirable for regions of the casting most distance from the liquid metal supply to freeze fast, and for solidification to progress from that remote regions towards the riser. Means in that cases we must be maintain the distance between riser and mold cavity. If distance is more, so in that cases the feeding of the molten metal maybe faces some problems. Okay. So when pouring molten metal goes to the mold cavity, so first solidification and liquid contraction takes place to that particular mold cavity. Okay. After taking the solidification, then it will take to that particular path between the mold cavity and riser. Then finally it will take the solidification to the riser. Before solidification to the mold cavity does not take place to the riser. If freezing start to the riser, then mold cavity, so the product after solidification to the mold cavity, finally the mold from the riser, the liquid metal does not come to the mold cavity. So first freezing start to the mold cavity. It does not take the freezing to the riser. Okay. And then molten metal continually available from the risers to prevent the shrinkage voids. The term solidification describes the aspect, freezing and methods by which it is controlled. Okay. Means solidification first starts to the mold cavity, then it will come to the riser. It does not take the freezing first to the riser. Okay. First the solidification start in mold cavity. achieving directional solidification. What happens in that cases? We have seen that as per Conniff's rules, we are design the casting itself, the orientation in the mold and the riser system that fits it to the particular mold cavity of the molten metal. Okay, locate section of the casting with lower volume ratio away from the riser, and so freezing occurs first these regions. Liquid metal supply for the rest of the casting remains open, means first solidification starts to the surface of across the mold surface, means more heat extraction will take place, then it will go towards the center. And sometimes we have used chills for easy heat removal or for quick heat removal. So when we apply the chills to the particular region, so that in that particular region more heat will be removed and it will start the solidification also in that particular surface also. So here we have seen that is the external chills. Okay, and sometimes we have used some internal chill also. Here we have used the external chills, means in that particular region more heat will be extracted in that particular region, and in that surface also start the solidification also. Riser design must be waste metal that will be separated from the casting and remelted to make more castings. Means sometimes some waste materials, means some extra material will be reserved to that particular riser. Okay, means after final product production, so in that cases again we have used that particular solidified product from that particular riser. Okay, again it will remelted, again we pour that particular mold cavity. Okay, another, to minimize waste in the unit operation, it is desirable for the volume of the metal in riser to be minimum. So it is required to notice that the volume area ratio of that particular riser must be minimum. Okay, otherwise more material will be wastage. Geometry of the riser selected to maximize the volume area ratio. So that type of shape we will be produced in case of riser. It will occupy the maximum volume area ratio. So in that particular thing we have poured the molten metal, and also it will hold the more amount of molten metal. So some mathematical calculations we have seen particular problem in the casting of steel under certain mold condition. The mold constant in Conniff's rule is known to be 4.0 meter per centimeter square. Based on previous experience or previous experiment, the casting is a flat plate. Okay, in figure 1 we have seen that, whose length L is 30 centimeter. L is 30 centimeter. With W equals to 10 centimeter, and height of that particular block H equals to 20 millimeter. Okay. Now using that block, first we know that total solidification TST equals to CM V by A whole square. Using that block we find out the area and volume. Area equals to 2LH plus 2LW plus 2WH, and volume equals to LWH. Using that formula find out we volume. Okay, and using that formula we find out the area also. So we are taken all the things in centimeter. That 20 millimeter also converted into centimeter, means 2 centimeter. 2 centimeter. Here we have seen that mole constant equals to Cm equals to 4 minute per semi square. All are in semi square. Now area after calculation using that formula, area equals to 760 centimeters. And using the volume formula, finally we have got 60 centimeter cube. Okay. Then as per Conniff's rule, we put total certification time CM V by A whole square. 4 into 600 by 700 whole square. Then finally we have got total solidification time equals to 249 minutes. Another cases, a cylindrical shape part shown in figure to be cast out of element, okay, aluminium. The radius of the cylinder is radius R equals to 250 millimeter. R equals to 250 millimeter. Okay. Its thickness means H equals to 20 millimeter. If the mole constant Cm equals to 2.0 second per millimeter square, all are in millimeter. In Conniff's rule, how long it will take the casting to solidify? So using same formula, we know total solidification time TST equals to Cm V by A whole square. Using that formula, we find out the total solidification time. So in case of cylindrical block, so area equals to, we know that a circular area is pi r square. That one part, that is the one part, that is the two part. So here area equals to 2 pi r square plus that circumference. Circumference means that circumference area equals to circumference 2 pi r into h. That is the total area of that cylinder. Volume we know pi r square is, that is the volume formula. Using that formula, we will find out area equals to, we put the all the things, then we finally have got 424,115 millimeter square area. And in case of volume, finally we have got 3926991 millimeter cube. And in the using that data, we put in case of Conniff's rule. Then finally we have got TST equals to 2.86 minutes. Okay, that is the final total solidification time in case of cylindrical shape part. Okay, to be cast out of elements. Means using aluminum molten metal, finally we have produced that type of cylindrical shape part. And end of this lecture, student has learned the concept of solidification of the metal and alloy and problems on solidification time. Now we have seen one video. What is directional solidification? Directional solidification means process of producing a casting that is free from voids or shrinkage defect by feeding the molten metal into the mold. In case of directional solidification, that is the mold cavity and pouring the molten metal through the getting system. Finally, it has come to that particular mold cavity. Means if we magnify, then that is the solid metal. So started means more heat will be extracted throughout the mold surface. Then it will start the solidification. That is the solid zone. That is the pasty mass of the metal. Means liquid phase it will maintain. Pasty mass of the metal. Means it is called massy zone. That zone is the liquid metal present. Means it will start the massy zone, means it will start the solidification. That are the three zones. Working of solidification process. Means more heat will be extracted throughout the metal surface. Due to more heat extraction, solid zone will be created. Massy zone, liquid zone and solid zone. That is the mold cavity. That is the riser and that is the pouring basin. The step by step from the sprue to the mold cavity, then it will come to the mold cavity, and then also some parts, some molten metal kept to the riser also, eliminating voids and internal cavities to that particular mold cavity. That is the directional certification, means it will start from pouring basin. Main part is the sprue, mold cavity, riser and mold cavity.